Chapter 3, Vectors. This lecture will help you understand how to work with vectors in standard position and apply the basic concepts of right triangle trigonometry using displacement vectors. Standard position when its tail is at the origin. A vector in standard position has a length expressed in terms of its magnitude and an angle theta measured counterclockwise from the positive x-axis. We will be using trigonometric functions, mainly the sine, cosine, and tangent. Remember the definitions of these functions. Sine is the opposite side divided by the hypotenuse. The cosine is the adjacent side divided by the hypotenuse. And the tangent is the opposite side divided by the adjacent side. Each vector can be considered the hypotenuse of a right triangle. A point P on the coordinate plane lies a distance from the origin. The distance is the length of the line segment OP. The distance is the magnitude of the vector. It is also the hypotenuse of a right triangle. The x and y components form the adjacent and opposite sides of the right triangle, respectively. We write the vector as P with an arrow over the letter. The x and y components, P sub x and P sub y, are found using the definitions of cosine and sine. The magnitude of the vector, its length, is written as the vector inside an absolute value. In vector algebra, this indicates the length or magnitude of the vector without direction. We will use this method when finding the x and y components of any vector. Given a vector with magnitude 16 and standard angle 212 degrees, what are the x and y components? First, draw the vector. Notice that the x component points to the left and the y component points down. This tells us that both components should have negative values. The magnitude length of our vector is 16 units and is at an angle 212 degrees. The x component is 16 times the cosine of 212 degrees, which is equal to minus 13.6. The y component is 16 times the sine of 212 degrees, which is equal to minus 8.5. Here's an application. A cable supporting a tower exerts a force of 723 newtons at an angle of 52.7 degrees to the horizontal. Resolve this force into its vertical and horizontal components. We call the vector F and note it has a magnitude of 723 newtons. The units of force. Note that we always include the units when discussing the magnitude of a vector, and the magnitude of a vector is always positive. We have to be very careful with this angle. The angle is given as 52.7 degrees with respect to the horizontal, but we have to think of the direction of the pull. Using an angle of 52.7 degrees actually would be pulling up, which doesn't make sense. We have to be pulling down and to the left. The arrow indicates the direction of the pull, that is the direction of the vector. This is opposite the angle of 52.7 degrees. This is 180 degrees opposite the 52.7 degree angle, so we add 180 degrees to it to get the direction of the pull, or 232.7 degrees. With that information, we can now find the x component of our vector F. It is 723 newtons times the cosine of 232.7 degrees, or minus 438 newtons. The y component of our vector F is 723 newtons times the sine of 232.7 degrees, or minus 575 newtons. Sometimes we're given the components of a vector and need to find the magnitude and direction of the vector. Here we have a vector r with the components rx and ry. Since the x and y components are the adjacent and opposite sides of a right triangle, we can use the Pythagorean theorem to find the magnitude. It is the square root of the sum of the squares. The direction we are looking for is the standard angle from the east. Now we use the definition of the tangent. The tangent of the angle is the opposite side, which is the y component of r, divided by the adjacent side, which is the x component. The angle is the inverse tangent of ry divided by rx. Two things to notice. The ratio ry divided by rx is given as an absolute value, and the angle is given as alpha, not theta. Alpha we will call a helper angle. It will help us find theta. We have to do this because of a limitation of the calculator. If ry is negative and rx is positive, we are in the fourth quadrant. If ry is positive and rx is negative, we are in the second quadrant. These are different angles. However, the calculator does not know this and always assumes fourth quadrant if the sign of either is negative. So we define the helper angle, which is the angle from the x-axis. We look at the sign of the two components of x and y. If both are positive, we are in the first quadrant. If x is negative and y is positive, we are in the second quadrant. If both x and y are negative, we are in the third quadrant. If x is positive and y is negative, then we are in the fourth quadrant. To find the standard angle, first calculate the helper angle alpha, keeping in mind that the argument is always positive. Then identify the quadrant. The standard angle is the helper angle in the first quadrant. In the second quadrant, the standard angle is 180 degrees minus the helper angle. In the third quadrant, it is the helper angle plus 180 degrees. In the fourth quadrant, the standard angle is 360 degrees minus the helper angle. There is also a helper angle, beta, which is measured from the y-axis. We will discuss this later. As an example, we have a vector b with components b sub x equal 10 units and b sub y equal minus 24 units. What is the magnitude and direction of vector b? Since b sub x is positive and b sub y is negative, the vector lies in the fourth quadrant. We draw the vector. The magnitude is the square root of 10 squared plus minus 24 squared, which gives us a magnitude of 26 units. Next, calculate the helper angle, which is 67.4 degrees. Since we are in the fourth quadrant, the standard angle is 360 minus 67.4 degrees, or 292.6 degrees. Study this diagram showing the addition of different component vectors. Direction is important when adding vectors. Given a real number c, we can multiply a vector by c by multiplying its magnitude by c. The direction of a vector does not change when multiplying by a positive scalar value. When multiplying a vector by a negative real number, it reverses the direction of the vector. Scalar multiplication with components. Once we have a vector in component form, the arithmetic operations are easy. To multiply a vector by a real number, simply multiply each component by that number. If v equals 3, 4, then minus 2v equals minus 6, minus 8. Vector additions can be combined. What was done with the vectors u and v? Vector u was multiplied by 2, and vector v was multiplied by minus 1. The two new vectors were then added. Vector addition with components. To add vectors, simply add their components. For example, if v equals 3, 4, and w equal minus 2, 5, then v plus w is the sum of the individual components, 1, 9. Other combinations are possible. For example, 4b minus 2w is 16, 6. A unit vector is a vector with magnitude 1. Given a vector v, we can form a unit vector by multiplying the vector by 1 divided by the magnitude of v. The purpose of a unit vector is to indicate direction, but not magnitude. A vector such as 3, 4 can be written as 3 times the vector 1, 0 plus 4 times the vector 0, 1. For this reason, these vectors are given special names. I is the vector 1, 0, and j is the vector 0, 1. Notice the little hats on top of the letters I and j. This indicates special vectors called the unit vectors. The unit vector I is in the direction along the positive x-axis. The unit vector j is in the direction along the positive y-axis. A vector in component form, v equal a, b, can be written as ai plus bj. A is the vector component in the x direction of vector v, and b is the y component in the y direction. The values a and b can be positive or negative. When two or more vectors are added, the sum is independent of the order of the addition. This idea is demonstrated by a runner practicing for a marathon along city streets. The runner executes the same 4 displacements in each case, but the order is different. Regardless of which path the runner takes, the runner will have the same total displacement. For these two examples, find the resultant magnitude and the direction as a standard angle. You should pause the video while you work. For practice A, did you get 11.2 kilometers at 116.6 degrees? For practice B, did you get 50 kilometers at 233.1 degrees? If not, make sure you ask during lab. As another example, find the resultant displacement of an airplane that flies 20 miles due east, then 30 miles due north, and then 10 miles at 60 degrees south of west. We will use the graphical method of vector addition. Choose a scale of 1 centimeter equal 5 miles so that the vectors are large enough to be accurate and small enough to fit on the paper. The length of the first vector is 4 centimeters and the direction is due east, to the right. The length of the second vector is 6 centimeters and the direction is due north, up on the paper. The vector is drawn from head of the first vector. The length of the third vector is 2 centimeters. The direction is 60 degrees south of west. The vector is drawn from the head of the second vector. The resultant vector begins at the tail of the first vector, which is located at the origin. It ends at the head of the third vector. Using a ruler, we find the length of the resultant vector measures 5.5 centimeters. Thus, the net displacement is 28 miles. Measuring from north, the angle is 24 degrees. The resultant vector is 28 miles at 24 degrees east of north. The same problem can be solved with the component method. Find the x and y components of vectors A, B, and C, which are shown in the table. Sum the x and y components of the 3 vectors to obtain the resultant vector r. And we get 11.3 miles as the x component and 25 miles as the y component. Both are positive. Then use the Pythagorean theorem to find the magnitude. of 27.4 miles. The helper angle is 65.7 degrees. Since both the x and y components are positive, the vector is in the first quadrant. The standard angle is the same as the helper angle. In the graphical method, we found that the angle of 24 degrees, but that was measured east of north. Now we are looking at the standard angle. The standard angle is 90 degrees minus 24, or 66 degrees. These values are close. When we do the graphical method, it is a good visualization tool. We can see the vectors. However, if we want accuracy, we should use the component method. For our next example, consider a novice pilot setting a plane's controls. Thinking the plane will fly at 250 kilometers per hour to the north. However, the wind is blowing at 75 kilometers per hour toward the southeast. What is the plane's resultant velocity relative to the ground? First, we find the x and y components of both the plane and the wind and write them in a table. We sum the x and y components to obtain the components of the resultant velocity. The x component is 53 kilometers per hour, and the y component is 197 kilometers per hour. Again, they are both positive. Then use the Pythagorean theorem to find the magnitude, which is 204 kilometers per hour. Our definition of the helper angle gives us 74.9 degrees. Since both the x and y components are positive, the vector is in the first quadrant. The standard angle is the same as the helper angle and is equal to 74.9 degrees. Your assignments for Chapter 3 are to read Chapter 3 in the textbook and do some of the problems for the problem sections 3.1, 3.2, and 3.3. These are listed on Blackboard.